Cocitation is the idea that we can infer similarity between nodes in a directed network by observing the structure of their connectivity. In particular, nodes that point to the same nodes are interpreted as being similar. And so one way to express that similarity is to build another graph, another network that encodes that similarity. So in the toy example from the book, we have two nodes, I and J, and we are looking, in cocitation, we are looking at the incoming edges to I and J. And so what counts are the nodes that point to both I and J. So nodes 1, 2, and 3 all point to I and to J both. And so for that reason, in the new cocitation graph, which is an undirected network, we will put an edge between I and J that has weight of 3. And so it's 3 because we simply have 3 nodes that point into I and J. You'll notice that I and J each have other nodes that may point into them. For example, this node points into I, but does not point into J. And so for that reason, it does not play a factor in the cocitation of nodes I and J. And again, this is rooted on the idea that nodes I and J are similar because the same nodes point to them. And so, for example, if these arrows represented friendship, then if 1 was friends with both I and J and 2 is friends with both I and J, then that starts to give the idea that I and J may also be friends, or they may at least be similar. And so this can also be the root, similarity can also be the root of things like recommendation engines. So now that we've seen the idea, let's move on and see how this works out mathematically. So mathematically, cocitation, what we want to do is we want to encode the same idea as what we just described, this idea that if two nodes have a bunch of common in-neighbors, a bunch of nodes that all point into the nodes of interest, I and J, that we're going to give that a weight equal to that number of nodes that point into it. So we can talk about the adjacency matrix of the cocitation network, Cij. So this is the edge between I and J. And what we said is that we want this to simply just be the count. So we're going to sum up 1 over the number of neighbors that are both neighbors to both I and J. So if it's a neighbor of just I, that doesn't necessarily count. It has to be a neighbor of both I and J. And so this expression of the index is rather vague. We write it out in English. We understand what it means, but now we need to encode that as a mathematical expression. And so one way that we often do this is that we use the adjacency matrix of the original graph. So the original graph is A, adjacency. It's a directed graph. So the edge IK means AIK. AIK means that there is an edge from K to I. If AIK is 1, then there is an edge. If AIK is 0, then there is no edge from K to I. And so we're using the sparsity of the adjacency matrix to do this sum that we wanted to do before. So now what we're going to do is we're summing up over all of the nodes, and we're going to rely on the fact that there are a bunch of zeros inside the adjacency matrix to make sure that we're not just summing up over all nodes. So in fact, we are only picking up nodes that have an edge from K to I. That's what this term encodes. And also from K to J. So a node indexed by K will be added to the sum if it has an edge to J and to I, which is exactly what we talked about as the definition of cocitation. All right, and now probably our first example of some linear algebra trickery, not too bad. We're going to rename or re-index the second term here. And we know that if we take the transpose of a matrix, we switch its rows and columns. And for that reason, if we take the K-A transpose and we take the K-jth entry, that is exactly the same thing as the matrix A and looking at the J-kth entry. So that's the same thing as transpose. And so if we do this, this sum over k now is a sum over this internal index, and this is what matrix multiplication looks like. So in general, we could have a matrix C that is equal to A times B, and if you wanted to look at the term Cij, this would be the sum over k1 to n of A and Ik bkj. So this is a generic formula for matrix multiplication, and so if you look at what this means, this is now that we have this internal k here that's saying that this is the multiplication between A and A transpose. And so the cocitation matrix is then A times A transpose. So that gives us a way of mathematically, using linear algebra, expressing the cocitation matrix rather than doing it with the graph. And so in the lab, you'll explore this. There is one step that we're leaving out in this linear algebra approach, and so you'll need to read the book to check on that. And then the other thing is that we're going to do the weighted extension. So the case where this is not just an unweighted graph, but now these edges have weights associated, weight 1, weight 2, and so on. And so these weights are going to be encoded. They're going to be the weights on the edges that do exist. And so you're going to need to use those in your program in order to construct the weighted version of the cocitation matrix. As an example, just to solidify the ideas, before you start your program, you should really make sure that this example makes sense. So what we're going to do is we're going to analyze, pick nodes I and j, and then see how many nodes are inbound to it. So if we look at nodes 1 and 2, we observe that 4 and 5 both point into 1 and 2. And so 1 and 2 are acting like I and j, and k being 4, we add 1, and k being 5, we add 1. And so for that reason, we add 2, a weight of 2 on the new edge between 1 and 2 in the cocitation graph. If we look at 1 and 3, we observe common inbound neighbors, and we see that 4 is a common in neighbor of 1 and 3, but there's no others. And so for that reason, we give this a 1, because 4 is the common in neighbor. If we look at, for example, 3 and 7, so 3 and 7, the in neighbors of 3 is just 4, and the in neighbors of 7 is 1. And so there are no common in neighbors between 3 and 7, and that is why there is no edge between 3 and 7. We don't have an edge here. And so you continue this process looking at all pairs of nodes and checking to see their common in neighbors. And this is how you'd construct the cocitation graph. I encourage you now to go back and make sure this makes sense in the book, and to also take a look at the very similar idea of bibliographic coupling. And I would recommend perhaps constructing the bibliographic coupling network from this example network to see what you get.